It is a well-known challenge for the current and future generations of engineers to find new ways to power our civilization that will not have such negative impacts on the long-term prospects for our society and our planet as fossil fuels. One of the many attractive ways to do this is wind power. However, wind turbines on land can be unsightly and noisy and do not take advantage of the much higher wind speeds over water. Building turbines offshore is an attractive solution, but several roadblocks have prevented this technology from reaching its full potential. These include the much higher cost of offshore foundations, largely because of the high moment loads from the wind and waves that need to be taken into account. In recent years, novel design ideas have been developed to address these issues.
Hi, my name is Kyle Reynolds, and I am between my second and third years as an undergraduate engineering student here at the University of Michigan. This past summer, I was given the excellent opportunity through the Summer Undergraduate Research Experience, or SURE program, to conduct academic research on the foundations for offshore wind turbines and different ways to model them. This was done through the Mechanical Engineering department, which I am majoring in. My research primarily consisted of learning about the field and different challenges within it. This was done with the end goal of working with my fellow researchers to compile a review paper about the state of the field and different ways to model the interaction of these wind turbine foundations with the soil they are installed in. Through this, we hope to gain a better understanding of what simplifications and assumptions can be made while keeping the model accurate. This will hopefully result in computer and equational models that are simple enough to be used in the design field, while at the same time accurately predicting the response of the system. Hopefully, this will result in wind turbines and with cheaper foundations that can power the future.
Traditionally, wind turbines in the ocean have been mounted by driving piles deep into the ground in a monopile or multi-pile design. A foundation design known as a gravity base has also been used, especially in shallower water. It simply consists of a wide and heavy base sitting on top of the seafloor. A more recent design uses one or more structures known as suction caissons. These are basically giant overturned steel buckets that are lowered to the seafloor, where they are then installed by sucking the water out, driving the device down into the soil. This installation procedure is far easier and less expensive. My research was primarily focused on the response of suction caissons to static and cyclic loads. The majority of research into modeling the static load response of suction caissons thus far has come through modeling and experimental verification of work hardening plasticity theory. This theory states that the stress versus strain graph, such as the one here, or an analogous force versus displacement one, will first follow elastic behavior before reaching a certain yield point. However, after that yield point, the plastic behavior that ensues is characterized by increasing stress needed for additional strain instead of a brittle or strain softening behavior. Another key feature of this behavior is that the unloading takes place elastically no matter how far past the yield point. This means that the yield point is permanently increased after high stresses. Most of the work in this area is consistent with using a two-dimensional approach that simplifies the modeling yet maintains accurate predictions. In this two-dimensional space, the loads present are a vertical load V, a horizontal load H, and a moment M.
These plasticity models require first a description of the elastic behavior before the yield point. This is typically accomplished with the simple linear Hooke's law relationship. Second, an equation for the VHM failure envelope. One major consideration here is to define exactly what the failure point is in the stress-strain graph. Third, a description for the flow behavior, a flow rule, after the stress has gone past the yield point. One common model used here is an associated flow rule, where displacements move perpendicular to the yield surface. And finally, a strain hardening expression to describe the expansion of the failure point after loads beyond this criteria. Much of the existing research has gone into the second point, the VHM failure envelope. For suction caissons, cyclic loading presents major difficulties in modeling. One particular question that arises is how cyclic loading over time affects the properties of the soil and therefore the foundation response. If there is very little effect, then traditional models and force-dependent models such as work hardening plasticity theory can still be used. However, if there is a major difference from static loading and the soil degrades over time when subject to repeated cyclic loading, then new models will have to be developed that incorporate this behavior.
This graph depicts the typical response of the system subject to cyclic loading tests, here on a moment versus rotation graphs. The loops here are referred to as hysteresis loops, meaning that the position of the object at any one time depends on the force at previous times. In this case, this means that when the force is reduced to zero, there is still some displacement from the initial position. However, the hope is that at least part of the curve, especially the maximum displacement that is critical for the overall design, can be modeled with a force-dependent model instead of a more complicated one dependent on past conditions. For graphs at this magnitude of loading, the cycling appears to increase the soil strength as evidenced by the greater moments needed to return to the same displacement in the graph. However, some other graphs show a constant return, while still others show a decrease in the moment necessary to return to the same position, indicating there that the cyclic loads have weakened the soil.
Taking all of this evidence into account, it seems that the apex of the hysteresis loops in the cyclic loading can be modeled with force-dependent models such as work-hardening plasticity theory, but only to a point. Much more research needs to be done as to where this point lies. If this point is well past the yield point of the foundation soil interaction system, then there is no need to consider this in a design application because the loads on this turbine should not be approaching this value anyway. However, if this point of cyclic data matching the static data is near the yield point or even before it, then more work needs to be done to develop models to incorporate this cyclic data for design use.
Another key topic in the modeling of cyclic loading on caissons is how the soil type affects the response. Comparing these graphs on clay and sand, it appears that both follow the hysteresis loops previously described, but the sand is much stronger overall. This is important because the same load in both sand and clay could be past the limit where force-dependent models are applicable in clay, but not in sand.
This research experience has been incredibly interesting and rewarding for me. It has been a great way for me to evaluate my interest in research and whether or not I would like to pursue a graduate education. I would like to take this opportunity to thank my advisory professor Bogdan Eperano, my fellow researchers Ki-Young Oh and Woo-Chul Nam, and I would also especially like to thank Shira Washington and all of the people with Shore who make this opportunity possible for so many students.